Hunter. We are the Group 6 and we are here to report Chapter 14 and our topic is all about the moment of statical stability.
Defining statical stability. The moment of statical stability is commonly referred to as the rightening moment at any given angle of heel is found, by which results from the buoyancy force being equal to the ship's displacement and it's acting on the end of the lever GZ, which fibers about G. The rightening moment at any angle of heel represents the instantaneous value of the ship's ability to return the upright expressed in tons meters. When the ship is in still water condition and it's momentarily at rest, acceleration forces as the ship roll are ignored. Statical stability. When a ship inclined by an external force such as wind and wave action, the center of buoyancy moves out to the low side, parallel to the shift of the center of gravity of the immersed and emerged wedges to the new center of gravity and underwater volume. The force of buoyancy is considered to act vertically upward through the center of buoyancy, whilst the weight of the ship is considered to act vertically downwards through the center of gravity. These two equal and opposite forces produce a moment of couple which may tend to right or capsize the ship. The moment is referred to as the moment of statical stability and may be defined as the moment to return the ship to the initial position when inclined by an external force. So, for example, a ship which has been inclined by an external force is shown in figure 14. The center buoyancy has moved from B to B1 parallel to GG1, and the force of buoyancy, which is labeled as W, acts vertically upward through B1. The weight of the ship W acts vertically downwards through the center of gravity, which is labeled as G. The perpendicular distance between the lines of actions of those forces GZ is called the righting lever. Taking moments about the center of gravity, the moment of statical stability is equal to the product of the righting lever and the displacement, or the moment of statical stability, which is equals to W times GZ. So let's move on. The moment of statical stability at a small angle of heel. At small angles of heel, the force of buoyancy may be considered to act vertically upwards through fixed point called initial metacenter, or which is labeled as M. This is shown in figure 14.2, in which the ship is inclined to a small angle, which is 0 degrees. Moments of statical stability is equal to W times GZ. But in the triangle GZM, GZ equals to GM sin theta degree. Moment of statical stability equals WX GM times X sin theta degree. From this formula, it can be seen that for any particular displacement at small angles of heel, the righting moments will vary directly as the initial metacenter height, which is GM. Hence, if the ship has a comparatively large GM, she will tend to be stiff, whilst a small GM will tend to make her tender. It should also be noticed, however, that the stability of the ship depends not only upon the size of the GM or the GZ, but also upon the displacement. Thus, two similar ships may have identical GMs, but if one is at the light displacement and the other at the low displacement, their respective states of stability will be vastly different. The ship which is at the low displacement will be much more stiff than the other. Example number 2. When the ship of 12,000 tons displacement is held 6 and 1/2 degrees, the moment of statical stability is 600 tons meter. Calculate the initial metacentric height moment of the statical stability is equal to W times GM times sin theta degree. GM, the formula for getting it is GM equals moment of statical stability over W times sen theta degree.
Pa.
So,
Na.
given the value 600 over 12,000 sin theta 1 over 1/2. So
Record.
the total answer is GM equals to 0.44 meters. Next, the moment of statical stability at a large angle of heel. At a large angle of heel, the force of buoyancy can no longer be considered to act vertically upwards through the initial metacentry, which is labeled as M. Next, then, this is shown in figure 14.3. Where the ship is held to an angle of more than 15 degrees, the center of buoyancy has moved further out to the low side and the vertical through B1 no longer passes through M, the initial metacentry. The rightening lever GZ is once again the perpendicular distance between the vertical through G and the vertical through B1, and the moment of statical stability is equal to W times GZ. But GZ is no longer equal to GM, sin theta degree. Up to the angle at which the deck edge is immersed, it may be found by using formula known as the wall-sided formula. GZ equals GM plus 1/2 BM tan squared 0 times sin theta. The derivation of this formula is as follows. Refer to the shape shown in figure 14.4. When inclined, the wedge WOW1 is transferred to LOL1 such that its center of gravity shifts from G to G1. This causes the center of buoyancy to shift from B to B1. The horizontal components of this shift are HH1 and BB2, respectively. The vertical components of being GH plus G1H1 and B1B2 respectively. Let BB2 be units and let BB1B2 be B units. Next. Now consider the wedge LOL1. Area equals 1/2 y squared tan theta. Considered an elementary strip longitudinally of length dx as in figure 14.5. Volume equals 1/2 y squared tan theta dx. The total horizontal shift of the wedge HH1 is 2/3 times 2y or 4/3 times y. Moment of shifting this wedge equals 4/3y times 1/2y squared tan theta dx, which is equal to 2/3y cubed tan theta dx. This is the wall-sided formula. Note, this formula may be used to obtain the GZ at any angle of heel so long as the ship side at WW1 is parallel to LL1. But for small angles of heel 0 up to 5, the term 1/2 BM tan 0 may be omitted. Example number 2. A box-shaped vessel 65 meters times 12 meters times 8 meters has kg 4m and is floating in salt water upright on an even keel at 4m drop F and A. Calculate the moments of statical stability at 5 degrees and 25 degrees heel. W equals LXB times X drop times 1.025, which is equal to 65 times 12 times 4 times 1.025 tons. And you will get W equals 3,198 tons. Next is you will get the KB, which is equals to 1/2 drop and Kb will, and you will get the Kb of 2m, and Bm equals b squared over 12d, which is equal to 12 times 12 over 12 times 4, and will finally get a Bm of 3m. So getting the Gm, by having the Kb of 2m, Bm equals 3m over 5m, Km is unknown, Kg equals negative 4m over 1m. Then, example number 2. At 5 degrees hill, Gz equals Gm sin theta equals 1 times sin 5 degrees. Gz equals 0.0872. Moment of statical stability equals Wg times Gz, which is equal to 3,198 times 0.0872, and equals to 278.9 tons m. At 25 degrees hill, Gz is equal to Gm plus 1/2 Bm tan degrees theta, tan squared theta sin theta, and equals to 1 plus 1/2 times 3 times tan squared 25 degrees, then sin 25 degrees, and you will get an answer of 1.3262 sin 25 degrees. Moment of statical stability is equal to W times Gz, and get 3,198 times 0.56. Then computing it, you will get a 1,790.9 tons m. Then the answer for the letter A is 278.9 tons m, and B is 1,790.9 tons m. The moment of statical stability at a large angle of hill may also be calculated using formula known as Atwood's formula. And this is the formula. Moments of statical stability is equal to W times V times HH1 over V minus BG sin theta. The derivation of this formula is as follows. Moments of statical stability is equal to W times Gz, or W times BR minus BT. So, let V the volume of the immersed or emerged wedge, HHL the horizontal component of the ship of the center of gravity of the wedge, V the underwater volume of the ship, and BR the horizontal component of the ship of the center of buoyancy. BT equals BG sin theta, BR equals Vx HH1 over V. Moment of statical stability is equal to V times HH1 over V minus BG sin theta.